Okay, good morning everybody. Today's lecture is continuation of previous lecture, that is like refrigeration cycle and their diagram and TS diagram and basic understanding of formulation. Okay, so today's lecture will start with components. So refrigeration cycle, you have seen the components like compressor you have, then you have condenser. So condenser releasing heat, then you will have one throttle valve, then you have evaporator. Okay, so after condensing it will be liquid. This is liquid and this is gas. Okay, and after compression it will be gas at high temperature. This is gas as at high temperature. So when temperature is reduced, so it will be forming liquid. Now it is having, you can see, four basic components. One is compressor. So this is compressor. So compressor normally it will be positive displacement type. Okay, if you can remember the previous lectures where we told that positive displacement type compressor or pump, it will be having higher pressure development capability and low volume handling capability. Okay, so in this case we need very lower amount of volume but higher amount of pressure we have to develop. That's why normally people will be using positive displacement type compressor. So positive displacement type compressor will have several types. One will be reciprocating type, another can be scroll, volute, scroll type, then screw type. Okay, so there are many types of positive displacement type compressors are there. So any one type can be used. Okay, for very small application, for very small systems, so scroll or reciprocating type compressor will be used. But in bigger cases where high volume flow rate you have to handle, in that case you can use centrifugal pump. Okay, so it will have higher volume flow rate capability, pressure development will be lower. So in that case maybe multiple staging will be required to develop required pressure, but at higher volume flow rate. What about the condenser and evaporator? So evaporator is taking heat from atmosphere, and this is actually copper coil. Okay, copper pipes, and fluid or refrigerant will be passing through this pipe. Okay, and outside refrigerant you put, outside this pipe you put your food item or fruit item, whatever you want to cool. Okay, so this, it will reduce your temperature sufficiently, and this is copper normally. So copper, because high heat conductivity. Okay, so again evaporator side, like if it is air conditioner, then hot the normal air will be passing over the coil, so air temperature will be going down. In refrigerator system, inside your refrigerator also small amount of air will be blown very slowly, but here flow rate will be higher, air flow rate. But in normal domestic refrigeration system or fridge, normally we say that fridge will be having lower volume flow rate in air. Okay, condenser also, it will be a copper pipe, again heat will be dissipated in the atmosphere. Okay, so this is condenser, this is actually evaporator. Okay, so many times the condenser will be air cooled or water cooled. Air cooled condenser, like domestic refrigeration system or fridge, this will be air cooled. But if you say big industrial system, the condenser will be like normally water cooled also possible. If you go to any cold storage and other big shopping malls, their cold storage outside some building, you can see lots of water splashing happening over pipes. So that is actually condenser for your refrigeration system. So they are reducing temperature using water splash. So water will take lots of heat, again splashing will create evaporation will again because of phase change, it will take lots of heat from the pipe and temperature will be lower. Okay, so expansion device, this is expansion device. or we say throttle valve. Okay, expansion device or throttle valve, we say it will be regulating pressure and flow rate. Okay, so regulating pressure. Okay, so pressure, let's say I have to put number, let's say 1 2 3 4. Okay, so 3 to 4 pressure will be changing, enthalpy not changing. Okay, so in that case you are changing pressure, and flow rate also you can control how much, because as per your requirement you can change your flow rate. Okay, so two type of expansion valve or throttle valve will be there. Expansion valve means like you create restriction in a pipe so that fluid flow rate will be reduced in the specific zone. Okay, and two types will be there, one will be variable type, another will be like constant restriction. So like for example domestic refrigerator or very low cost systems, they may not have many options, but if you have a high quality or high end refrigerator or air conditioning system, there will be multiple options actually, very variable restriction, variable flow rate. So because they will be optimizing your energy requirement and noise production. Okay, in compressor system, the name is compressor, so it will not be handling any liquid. So normally you have to give gas, or after evaporator everything should be gas, then you are putting that gas into compressor system, then you are compressing, releasing heat in condenser, it is passing through throttle valve. Throttle valve, it will be reducing flow rate and it will be changing pressure, but enthalpy will be same because you are not adding or removing any energy from in the throttle valve. Okay, then evaporator system, it will have the coil, copper coil, so it will be absorbing heat from surrounding, or if it is air conditioning system, then air will be blowing over the coil, so air will be cooled down and it will be circulated inside your room. Okay, reciprocating system also, there will be a single, like reciprocating pump or compressor, it will be having single cylinder or multiple cylinder. Okay, if you have single cylinder, then it will be very small system. Multiple cylinder means maybe intercooler may be there, so that you can reduce temperature in between compressor and you can improve performance of the compressor, so that your power performance improves. Okay. Okay, volumetric efficiency of reciprocating compressor. Volumetric efficiency of reciprocating here in this system, vapor compression system, you see the term is compression is there, and compressor is the heart of the system. If compressor function, any problem in the compressor, that means whole system will fail. Okay, so volumetric efficiency of compressor, eta volume equals actual volume divided by piston displacement. So you can remember that reciprocating pump or compressor. Okay, so actual volume means you measure using instrument and you see how much volume flow rate you are getting. Okay, that is your actual volume flow rate. But piston displacement volume means, like if you know diameter, you know stroke length, forward backward motion, that length L, so this volume is equals pi by 4 d square into L. Okay, so this is piston displacement volume. So if you know actual volume, how much it is delivering, how much piston is delivering, piston is moving, so that ratio is called volumetric ratio. And why the actual volume will be lower? Sometimes piston will have certain leakage also. Because of leakage, volumetric efficiency will be lower. If it is sealed properly, then volumetric efficiency will be very much higher. But weared out any compressor piston, so their volumetric efficiency will be lower. So volume of gas handled by a compressor, volume of gas handled by a compressor equals omega V1 meter cube per second. Okay, omega is so mass flow rate in kg, m mass flow rate kg per second, volume is kg per meter cube. Specific volume, specific volume will be meter cube per kg, meter cube per kg. Okay, now WV1 equals pi by 4 d square L, d I should write capital D, d square L n by 60 into small n. Okay, eta volume. Okay, so here cylinder diameter already I have shown in figures, cylinder diameter. This is stroke length, n GTH. N is RPM, revolution per minute. Small n is your number of cylinder, and eta volume already we defined volumetric efficiency. In this way we can calculate volume of gas handled by a reciprocating compressor which is having multiple cylinder, maybe, or one cylinder also possible, because based on value of n we can calculate. And whenever you are calculating, you have to see the units. Unit must be balanced, left side or right side. Okay, these topics are taken from NPTEL-NOC book. So multi-stage compressor. If you have seen single stage compressor system, so now if we put it to multiple stages, then system performance will be much better. So how this will work? You have one evaporator condenser system, then you have one compressor. This is condenser releasing heat Q1, and after condensation fluid is going to one throttle valve, then it is going to one evaporator section. From evaporator it is going to again compressor. This loop already you are familiar with. Okay, so numbering I will be putting later. I have another loop actually, another compression system, evaporator system, then from evaporator throttle valve is here. Okay, so you can say multiple stage, two compressors are there and they are cooling one evaporator section, evaporator. Okay, so heat is being given there, Q2, heat is taking from surrounding, and this is called direct contact heat exchanger. Okay, this one direct contact heat exchanger, and M1 mass is circulating here, M2 mass circulating here. So two cycles are there, top cycle, bottom cycle. Top cycle mass circulation or refrigerant cycle. The top cycle has refrigerant circulation rate M1 dot, and bottom cycle M2 dot. Okay, and now put the numbering. Numbering before compressor 1, here 1, after compressor 2, then it is going to one direct contact heat exchanger, it is going to 3, then 3 to 4 after compression, 4 to 5 it is going condenser, 5 to 6 it is going, 6 to 7, 7 to 8. You can see the top cycle is reducing certain temperature, that temperature, that heat, the top cycle releasing certain amount of heat, that heat is being used by bottom cycle, so that you are getting more effectiveness in evaporation. And what will be the intermediate pressure? Pi equals P1 P2 square root, and pH diagram I will draw here. So 1 to 2 compression system, 1 to 2 compressor, 2 to 3 what is happening? It is absorbing certain amount of heat 3 2 1, the 3 to 4 again expansion compression happening, 3 to 4, 4 to 5, what happened, 4 to 5 heat release happened, then 5 to 6 throttling happening, then 6 to 7 again some temperature increase is happening in bottom fluid, 7 to 8 throttling happening, 8 to 1 the process is becoming complete. P1, this is P2, intermediate pressure is Pi. Okay, this is mass M1 dot, this is mass M2 dot. Okay, so two cycles we have different mass flow rate in the cycles. Okay, now if you see the direct contact heat exchanger, so their heat balance I will do there, M2 H2 where is 2? Okay, here M2 after compression M2 H2 plus fluid is entering here, another entering is coming from 6, so M1 dot H6 equals fluid exiting 3, H3 M1 dot plus exiting 7 also M2 dot H7. Okay, so total heat balance I have done, total amount of fluid entering, total amount of fluid exiting. Okay, so M1 dot by M2 dot, if you rearrange the equation, it will be coming like H2 minus H1, H3 minus H6. Okay, now M2 dot H1 minus H8, you can see the evaporator effectiveness, it will be like 14,000 divided by 3600 into P. This you have to remember the formula, P is your ton of refrigerant, of refrigeration. Okay, so from here you can calculate M2 value, or you can say P is a capacity. Okay, okay, another topic is the cascade system. Cascade system where two fluid will be separated 40 degrees centigrade, let's say condenser temperature. Okay, condensing will be happening constant pressure and constant temperature, and we have one compressor system. Compressor means like, now this is turbine, compressing here. Okay, then it is going to one heat exchanger, throttle valve is here. Okay, then another I have heat exchanger happening, throttling will be happening, then evaporation will be happening, then I have one compressor here. Okay, so I can have multiple stages, so this is called cascading system. Okay, so let's say this is one cycle, this is two cycle, or A cycle, B cycle, just I put minus just my own name, minus 20 degree, just example temperature, so it may not be only fixed 40 and 20 degree, it may go to minus 180 degree also. Okay, this is C, compressor A, compressor B, and if I want to draw in pH diagram, so pH diagram will be little bit tilted actually, this is saturation curve. Okay, so 6 to 7 compression happening, 6 to 7, 6 to 7, then 7 to 8 throttling happening. Throttling means I will put dotted line, 7 to 8, 7 to 8, then 8 to 5, 8 to 8 to, it is going to 5. Okay, 8 to 5, 6 5, okay, 8 to 5, then my compressor. Okay, this is top cycle, this is B. Now bottom cycle, it will be taking heat from top cycle condenser, evaporator is bottom cycle's condenser. right? So this is heat exchanger. HE means heat exchanger. Okay. Now top cycle temperature should be lower okay 2 after compression 2, then before compression 1, then 3, 2 to 3, 3 to 4. Okay, so you can see this bottom cycle condenser temperature. Oh, this is pressure. Okay, so it doesn't matter. Oh, this is pH diagram. Okay, fine. Till now we discuss only VCRC, vapor compression refrigeration system. VCRC, vapor compression. This is compression. Okay, this is cycle. Sometimes I write VCRS also. S means system. Okay, so now I will discuss VARC, vapor absorption system. Okay, basically two types of systems will be there. One will be ammonia refrigerant system, another will be water refrigerant system. Okay, how the system looks like? It will have again condenser. Okay, so condenser fluid will be throttled, then it will be going to evaporator. Okay, up to this it is common as this is VARC, vapor absorption system. Now vapor compression system, you can remember I have throttle valve, condenser, then evaporator, compressor. Okay, you can see the resemblance VCRC. Okay, you can see the resemblance. This left side part almost same, right side part for VARC will be different. How? There will be absorber, then there will be one generator, then from absorber to generator one pump must be there. Okay, fluid will be pumped to generator, and from generator one throttle valve will be coming here and it will be coming to absorber. Okay, so you can see this right side part, this part is different. Than a VCRC. Okay, now how this ammonia and water refrigerant will be working? So in this case, if it is ammonia, let's say ammonia is circulating, so what will happen? Ammonia circulating, ammonia in evaporator, it will be evaporated, it will go to absorber, absorber will be absorbing ammonia. Absorber means it will be water. Okay, absorber will contain water, so water will be absorbing lots of ammonia vapor. When it is absorbing, it will create low pressure. So when it is creating low pressure, so normal ammonia, liquid ammonia will be evaporating. Okay, then this ammonia and water mixture, whatever you got, you have to pump to generator. Generator, you give lots of heat. Okay, in generator you are giving lots of heat and you are isolating water and ammonia vapor. Okay, then ammonia, what will do? Ammonia will move towards condenser. Okay, ammonia is moving towards condenser and it is going to throttle valve to evaporator. Again ammonia going to absorber, absorber will be absorbing ammonia. Okay, now what is this throttle valve? Second throttle valve. So from generator to absorber, so generator to absorber means after releasing ammonia, this higher amount of water, the water will be coming down to absorber again, so the whole system will be continuing. Okay, so if we have water as a refrigerant, in that case what happens? In that case, water or H2O refrigerant, in this case what happens? Water is absorbed by lithium bromide solution, LiBr solution, LiBr. Okay, so water will be circulating, lithium bromide will be absorbing in the same process as ammonia cycle is there. Okay, now formulation for vapor absorption refrigeration system, COP and other parameters. So source T1, from source it is going to generator to condenser, then absorber, evaporator, then you have QE, region of TR means refrigerant. So I have to draw this vapor absorption system again. Condenser, generator, then condenser to throttling valve, then evaporator system, then evaporator to generate absorber. So absorber to generator, it will be going through a pump, and generated to your absorber again. When it is coming back, it will be coming back through one throttle valve. Okay, so whenever you are drawing for your exam, you should give proper arrow direction also, so that you can get full marks. And evaporator is taking heat QE at temperature TR, refrigeration temperature, and let's say ammonia circulating and ammonia liquid here after condensation, and after throttling ammonia will be absorbing heat, then it will be creating vapor ammonia. Okay, then when it is pumping, it is rich mixture. When it is coming down, there will be basically water. Okay, and from generator, ammonia going, ammonia at higher temperature. Okay, so condenser releasing heat QC at T2 temperature. We are assuming generator is getting heat, so at high temperatures fluid, water and ammonia will be separated, so QG, and temperature T1, and pump, one pump is here, so pump will be pumping liquid thing, it will not work in the gas or steam, so only liquid will be pumped. Okay, absorber is having cooling water also will be coming, so this is QA at temperature T2. So this is ammonia plus water cycle. Okay, now I'll make one control volume here, evaporator. Okay, so condenser, then pump will be working here. So vapor absorption system, only air, basically mechanical energy input will be there from pump, other parts are getting like waste energy. This vapor absorption system, good thing is that like it will be taking heat or releasing heat from in the surrounding, and especially like solar air conditioning system, there in basically heat is required in generator section, when where you are separating your ammonia and water, or water and lithium bromide, so heat is required. So that heat may come from your waste heat sources. Anywhere there is any waste heat, you can use. Solar power plant, they are can be small amount of it that can be working also, and electricity requirement in pump is very lower amount. But in vapor compression system, electricity requirement will be very high, and it is not depending on any other waste heat or other heat. Okay. So heat absorbed Qg, source T1 by generator, and QE evaporator heat absorbed TR from TR, rejected heat QA and QC, QA at absorber and QC at your condenser. So absorber also rejecting and condenser also rejecting, but heat is getting absorbed in generator and evaporator. Okay, now heat balance you can do Qg plus QE, heat absorbed, equals QA plus QC. Okay, and second law of thermodynamics says del S source equals del S sink plus del S region greater than equals 0. Okay, so minus Qg by T1 plus QE plus Qg T2 minus QE by TR greater than equals 0. So or Qg by T1 plus Qg by T2 so Qg by T2 plus QE by T1 minus QE by TR greater than equals 0. So from there we get T2 minus TR, T2 TR QE less than equals T1 minus T2 T1 T2 QG. So QE by QG less than equals T1 minus T2 T2 minus TR by T1. So COP equals QE by QG less than equals T1 minus T2 by T2 minus TR by T1. So maximum COP equals T1 minus T2 T2 minus TR by T1. Okay, so this is the formula for your maximum COP you can get from your vapor absorption refrigeration system. Okay, now you see vapor absorption and vapor compression system we discussed. What are the difference actually? So vapor compression system, you can remember it is having compressor, condenser, throttle valve and evaporator. Basically some more other system also there, but basically key parts are there: compressor, condenser, throttle valve, evaporator. But in vapor absorption system, actually you replace this compressor and you put absorber, generator and one extra throttle valve also you added, actually one pump and one extra throttle valve also. Okay, so this section is replaced by this one. Okay, and vapor compression, when you're talking about, the compressor is actually noisy. So because it is using a huge amount of energy and it is compressing gas, so it is more noisy. But vapor absorption system less noisy. Refrigerant normally CFC, HC, HFCs will be used. Vapor absorption normally NH3 or H2O as a refrigerant. Okay, so here you can remember H2O is refrigerant when lithium bromide LiBr is your absorbent. Okay, H2O will be absorbed by LiBr. So this is absorbent, absorbent, and ammonia absorbent will be water. Water is the absorbent for ammonia. absorbent, AND, E, BANT. Okay, so H2 is absorbent, correct? Oh. Okay, so H2 is the absorbent for NH3. Okay, spelling is NT. Okay, wear and tear in compressor. A small wear and tear will be higher in compressor because this is taking lots of energy, and this is the main part of the system, and it will be working continuously. Small pump, low pressure handling for vapor absorption system. Refrigerant in vapor compression system is compressed, but in vapor absorption system it is absorbed. Okay, this is difference from name itself, it is there. Operating cost for vapor compression system is higher because one compressor is continuously working, but VARC or absorption system, in that case only small pump is working, other pump is non-moving element, so life will be longer. COP for vapor compression system is higher, but VRC is having lower. For vapor compression system for window air conditioner or split air conditioner, so normal application is very commonly used, but for very large application vapor absorption system is used. Vapor absorption system is already heavier, so small application room air conditioning is not suggested to use this vapor absorption system. So another term is there, cryogenics. So if you go to IIT Kharagpur website, I think they have a master's program in cryogenics. So cryogenics is used for rocket propulsion, fuel, and other aspect. So science of low temperature. The term is coming from Greek word cryos and genic. So frost creation or production. Okay. So low temperature science is called cryogenics. So it can produce, let's say, minus 180 degrees centigrade temperature also. Okay. So commonly application liquefaction of nitrogen, oxygen, or any gas. You can create liquid, carbon dioxide liquid. You can create using this so low temperature. Again, one single compression system, vapor compression or absorption system will not create that temperature. So you have to do cascading. So one will be maybe reducing 50 degree, another 50 degree, another 50 degree. So that way 2-3 stages you can make, and then you can create such low temperature. Okay, so producing and storing superconductors, studying low temperatures phenomena, and many other things done through cryogenics technology. Okay, thank you very much for today's lecture. Next day we'll start sensible heating and cooling and humidity related thing, and we'll solve some problem and we'll close the chapter. Thank you very much.